Welcome to the 2023 RSNA Imaging AI in Practice demonstrations. My name is Ali Tijani, and I'll be your guide for portions of the upcoming demo.
Hi, my name is Madhavi Devuri, and I'm a radiology resident at the University of California, San Francisco. Today we'll walk through the clinical scenario of a patient, Francine, a 47-year-old female, who comes into the ED for shortness of breath. All of you should recognize that this is a PACS system. The demo will focus on this system with which we are used to working every single day. In this case, we're focusing on the Paxera PACS system. Our patient Francine presents to the ED with shortness of breath and is found to have an elevated white blood cell count and D-dimer. Her ED doctor orders a chest radiograph. The image is acquired and sent to the Paxera PACS for storage. The study is also sent to the MONAI AI orchestrator, which acts as a traffic cop and distributes the study to the appropriate AI algorithm, in this case, the Siemens AI RAD Companion Chest X-ray tool. Before we review the study, a quick note on MONAI. MONAI is an open-source framework supported by NVIDIA in collaboration with several institutions, including King's College London, Mount Sinai, and the Mayo Clinic. MONAI is specifically designed for building and deploying medical AI applications. Okay, back to our radiologist in the busy shift. The radiologist notices that the study has been prioritized to the top of the stat list on the Siemens Medicalis Workflow Orchestrator work list, and is marked with an AI flag suggesting a critical finding. The radiologist clicks on the chest X-ray on the list and on the AI result. Francine's chest X-ray shows a wedge-shaped opacity at the peripheral right lower lobe. The Siemens AI RAD Companion Chest X-ray tool correctly places a bounding box surrounding the opacity and identifies it as a consolidation. The Siemens AI RAD Companion Chest X-ray can identify a pneumothorax, pleural effusion, consolidation, atelectasis, and pulmonary nodules. The radiologist thinks this opacity may represent pneumonia, but remember that the patient had an increased D-dimer? Then this wedge-shaped opacity, well, it could actually be a pulmonary embolus. The radiologist can proceed to dictating the study and recommends a CT-PE, or pulmonary embolism, to evaluate for it. Before we move on to the CT, I know I have been talking a lot about sending images to Paxera PACS and the MONAI AI orchestrator, as well as the Siemens AI RAD Companion Chest X-ray tool, and so on and so forth. Qvera, an important player that does a lot of the behind-the-scenes work and a key component of interoperability, allows for this to happen. Many people probably know that these systems, PACS, EMR, reporting software, speak standards like DICOM, HL7, and FHIR. The Qvera interface engine acts as a translator between these standards to ensure all of these systems communicate effectively and makes everything just work.
Back to our clinical story. If you recall, Francine had an elevated D-dimer, and her chest X-ray results prompted the CT chest. The images for the CT are acquired and sent to the Paxera PACS for storage, and MONAI's AI orchestrator, which routes the CT study to the Telerad Tech PE Assist tool. Since Telerad Tech PE Assist tool flagged this study on the work list not shown here, our radiologists know to open it as soon as possible to review potentially urgent findings. When we click on the AI results button in the PACS, we're then taken to the Fovea Extreme AI Cockpit Viewer from the PACS, where we can see Francine's CT study with the relevant AI findings. The Telerad Tech PE Assist tool allows us to determine are there positive or negative results for pulmonary embolus. If positive, we see segmentation masks placed over the pulmonary emboli. We can also assess right heart strain with automated calculation of the right ventricular to left ventricular ratio. Here we see that the tool has provided an RV to LV ratio of 1. Just to make sure that there truly is no right heart strain, we also review the images and confirm that this is in fact a true finding. We can then also review a list of all the emboli and their locations displayed here in this panel. The radiologist can subsequently click through each listed embolus to accept, reject, or modify the findings. After confirming or rejecting all findings, the radiologist can directly export results into Nuance's PowerScribe 1 and finish dictating the remainder of the study. Because the AI results are coded in the RadLex lexicon and other coding systems, the AI results are easily and automatically populated into the report template. Note that none of these measurements or observations were dictated by the interpreting radiologist. We'll show a new paradigm here with the imaging AI in practice demonstrations. As you see, this report may look different than what you're used to seeing back home. Here we're following the interactive multimedia reporting profile from the IHE. Those reviewing the report can click on the series and image numbers for certain findings to navigate to representative images showing the finding in question. For example, by clicking on the hyperlink for this pulmonary embolus, we navigate to the representative axial image.
Okay, back to our clinical scenario. Francine receives the appropriate care for her pulmonary embolism and is subsequently discharged. She follows up with her PCP and is scheduled for her annual routine screening mammogram. Her mammogram is acquired and sent to the Hologic Mammography AI tool for analysis. On the Siemens Medicalis workflow orchestrator, we can see that a mammogram needs to be read, and we can view the AI results to the Hologic AI viewer. The Hologic Mammography AI tool has identified a mass in the right upper outer breast with a confidence score of 85%. We can see where the AI results are on the 2D and tomo images, and that there are also calcifications that are found in the left breast. The radiologist is able to interact with the results and can toggle the AI findings on and off. The AI findings in this case are not automatically shown on the PACS or on the DICOM for the study. The radiologist dictates the results. In this case, because of the suspicious mass, it's a BIRAD 0 for a callback, and a diagnostic mammogram with a breast ultrasound is scheduled. Throughout this demo, you might have noticed that all of the applications such as PACS, image viewers, and reporting open correctly to the same patient. This is possible using a standard called Firecast, which is different from FHIR. Firecast coordinates applications to look at the same patient securely. Firecast, in short, is a standard that synchronizes clinical applications such as the EHR, PACS, reporting systems, AI tools to a given study or patient. Upcoming versions of Firecast will also be able to exchange measurements and AI findings.
Moving on to a non-interpretive use case, our patient can access her own imaging and report through Pocket Health, keeping her engaged as an active part of her treatment team. Let's log on to her account. Instead of having to return to the hospital for a CD, Francine logs into her Pocket Health account where her medical imaging and reports have been automatically uploaded. Now, let's open a report. This is the Pocket Health Report Reader tool, which defines complex medical jargon in layman's terms, so the patient can understand and stay informed of her own health. Here we can see that the term embolus is defined as a blood clot in more patient-friendly language. One of the most important components of the report for the patient to understand are the critical next steps noted in the impressions. Pocket Health's MyCare Navigator automatically extracts this recommendation for follow-up, in this case for breast imaging, that may be hidden in the dense report, and highlights it on the right-hand side. It also provides the context. Thanks to Pocket Health's MyCare Navigator, Francine was able to schedule her follow-up. As Francine prepares for her next appointment, she can also reference Pocket Health's Ask My Doctor, which provides potential questions based on the report relevant to her care.
Okay, so throughout this demo, we've seen several different AI tools. So how do you decide which tools to procure for your practice? This is where MDAI can help. MDAI is a cloud-based annotation model validation platform. Users can securely manage and annotate their imaging data, deploy models, and review model predictions in a collaborative way. Here's a project comparing the performance of two different pneumonia AI models. The idea is to evaluate the AI model's performance in real time and on any data to make sure they are safe and effective before they can be adopted for your clinical practice. On the left side, you can find labels associated with model outputs organized by label groups. First, we as a radiologist are going to create a ground truth. Click this label and draw a bounding box around what you think is a pneumonia. Under models, you'll find two pneumonia detectors deployed to this project. Let's go ahead and run them. You can see them processing, and now the model's predictions are ready for review. Looks like they have both identified a pneumonia around the same area. You can copy the model output as an annotation, which we call model-assisted annotation. This way, you will always have the original model outputs at the bottom as a reference. MDAI has also made federated model validation possible. You can easily clone and test a model across different projects on MDAI without sharing data or the model source code with your collaborators. Now, we are going to launch MDAI Reporting and Chat app. This is designed for report generation and sharing powered by large language models such as GPT-4 and Llama. Today, we are just leveraging the tools to analyze model performance. Assume we are comparing results from 10 exams to assess the performance of each model over multiple exams. Through the MDAI Python library, we can download all the annotation model output data, including the bounding box coordinates, which are presented in a table. On the right side, we have a prompt to analyze the data and identify the better model. As you can see, GPT-4 is referencing the context we have provided on the left. Within seconds, you'll know which model performs better. Let's say I also want to email the results to another doctor for review. You can click Infer email of recipient, and GPT-4 will automatically retrieve the email for the physician from the report on the left side.
We hope that you consider the following takeaways from this demonstration. The architecture of your overall system for the hospital is critical. Requiring international standards such as IHE, DICOM, and HL7 Fire will enable interoperability. Requiring structured, coded semantic systems such as Radlex, Loink, and SNOMED will make the AI and other data flow through your system seamlessly. And finally, you will need to ask for all of these standards in every RFP for every system. Benefits shown in this demo include how AI models can improve your workflow, image interpretation, and reporting, and also how we can use new tools to improve and compare existing models that work best for our specific practice. Thank you for your time. Please review the other 2 demonstrations as part of this series.